Okay, so I'm going to go straight to problem number 2. So problem number 2 states a flow field is formed from a superposition of two canonical flows, a uniform flow and the source at the origin. Find the stagnation point or points and write the equation for the pressure at any point in the flow field. Okay, so first things first, I want to investigate what is my flow field made of. So my flow field is basically made of two flows. I have a uniform flow and the source. This is the basic information I need to tackle this problem. So I have a uniform flow and the source. Okay, and then I continue with the question. I need to find the stagnation point or point, so that's one part of the question, and I have to write the equation for the pressure at any point in the flow field in terms of P naught, U and V given far away from the system. Okay, again I will do exactly the same thing. I will construct my flow field from a combination of stream functions or velocity potentials. So I will go up to my table. I will investigate. I have the uniform flow, so potentially I can use this and this together, or I can use the stream function, this and that. Again, as I mentioned, and that's a personal preference, I would not work with this guy. Okay, if you want you can work, but I would not. So I'm going to go ahead and work with the combination of stream functions. It is very important to know that when it's a source, M is plus, and when it's a sink, M is negative. So a small negative number adds here, but right now we're dealing with plus, so this is plus because it's a source. Also, all these questions are asked at the origin. When it's at the origin, we can use these relations straight away. When it's not, we cannot use them right away. We have to do some modifications to account for the fact that our sources and sinks are moving away from the origin. So let's solve this problem. So number one, I will use the stream function. So I have phi xi actually is a combination of the uniform plus a source. Okay, so I would have here, if this is my flow, and let's say this is my coordinate system. I have a source here, okay. Now my angle alpha, obviously with the uniform flow, is 0. So if I go up here and replace 0 in my stream function, I will get sine of 0 is 0, so I'm going to end up with y uy. And plus for the source will be m over 2 pi theta. Now remember, as I mentioned, you cannot work with y and theta. You cannot work with Cartesian coordinates and cylindrical coordinates at the same time. So you must change one to the other. Okay, so I will change my y to Cartesian coordinates. So I'm going to have ur cosine theta plus m over 2 pi theta. All right, so this is my first milestone. I'm done with my step 1. Are you sure I get some partial marks for this? Now, step 2, I'm going to have to find, according to our steps here, u and v, or vr and v theta. So we're working in cylindrical coordinates, so basically I'm going to find vr and v theta. Notice the question doesn't tell you find vr and v theta. The questions right away tells you find my stagnation point and find the pressure. So anyhow, I'm gonna have to find the VR and the V theta, so I will do this automatically. So for the VR, if I'm working with the stream functions, it's in 1 over r d psi by d theta. So this is gonna give me, after differentiation, u cos theta plus m over 2 pi r. And for v theta, I have minus d psi by dr. So I have minus u sine of theta. Okay, so here I can say Vr is u cos theta plus m over 2 pi r, and V theta is minus u sine theta. Okay, so that's second part. I would box this and I ensure some partial marks. Now, part 3, which is the actual question, the first part of the actual question, find the stagnation points. So in order for me to get stagnation points, okay, so what is the stagnation point? I must have Vr equals 0 and V theta equals 0. Okay, now I'll start with the easy one, this guy. So I'll take V theta is minus u sine theta is 0. Okay, so which is the case when my theta is 0 or pi? Okay, good, excellent. Now I will go back here to my graph, and we also did this in the lab, and we know that when we have a source and a uniform flow, the actual shape is going to look something like this. So we're going to be creating somebody like this. Now the flow is approaching, and obviously this is my theta angle going in the counterclockwise direction, and I'm finding theta 0 is a possibility and pi is another possibility. But if I inspect, I would see that when theta is 0, there is no way for me to have a stagnation point, because my approaching u is in the direction of the source. So actually this, at this point, my flow would go faster. So the only possibility for me to have a stagnation point is somewhere at this point, when this vector and this vector meet. That's the only time I'm going to have a stagnation point. Therefore, the only acceptable possibility is when theta equals pi. Now, knowing this, I can go and place this in my Vr is u cos theta plus m over 2 pi r. Now, if I replace pi for theta, I'm going to get u cos pi plus m over 2 pi r is 0. So I'm going to get minus u equals minus m over 2 pi r. Therefore, r is m over 2 pi u. So here are my two stagnation points. Therefore, stagnation point is at m over 2 pi u and pi r and theta. Okay, now moving forward, I have to calculate the pressure or give an expression for the pressure at any point. So right away when I hear pressure, velocity, and I'm dealing with velocity potentials, I know that I'm going to have to use Bernoulli. So my V squared is Vr squared plus V theta squared. So I have u squared, straight up from the functions up there, I have u m cos theta over pi r plus m over 2 pi r squared So I'll apply Bernoulli. P naught plus 1 over 2 rho u squared equals P plus 1 over 2 rho v squared. This is given, and this is actually this guy here. Therefore, I have P equals P naught plus 1 over 2 u squared minus, let's see here, so we need P naught, so u squared minus v squared, which v squared is actually this part here. Now, for the stagnation point, notice that the stagnation point occurring at this point here, we have m over 2 pi u and pi. At this point, what is m? M is the intensity of my source. So as m increases, my point will move further this way, right? Because that's the radius r. So as m increases, you'll be able to push the stagnation point to this point. And if u increases and m is constant, the stagnation point is going to get closer and closer to the sink. So our stagnation point makes also sense. So that's the second problem, and I'm going to try to see if there's another relevant problem. I'm going to upload that as well.